What's up YouTube? In one of the previous videos we talked about agentic workflows. This one's a follow-up, but now I'm going to walk you through 5 workflows in one go, and we are going to keep it simple and snappy. For each one, I'll explain what it is, when to use it, and how to build it using code. These workflows are based on research by the Anthropic team, and they're super useful to understand whether you're coding your own agents or even building them using no-code tools. If you watched the last video, you can skip the first workflow, but if it's your first time here, stick around, you'll learn a lot. So let's get started with prompt chaining. The flow begins with a simple user request. It could be something like generate a summary, analyze a difference, or even respond to an email. This kicks off the first LLM call. Next, we'll reach a gate. Think of it as a checkpoint to decide whether the result is good enough to move forward. If it doesn't pass, then we exit. However, if it does pass, we continue the process and move on to the next LLM call and the next one, depending on how many there are. The final result is a clean, accurate output, which is the whole point of chaining. Chaining works best when you have structured tasks that can be broken down into clear, fixed steps. Accuracy matters more than speed or latency, and you're working in a multi-stage workflow like summarizing, checking, and transforming content. Now let's take a look at the code and see how we can recreate it using Vercel's AI SDK. We start by importing the relevant modules from the AI SDK. In this case, it's OpenAI and Generate Text. Generate Text lets us send prompts to the model and get back a simple text response. Then we initialize the model. In this case, we are using GPT 4.0. Next, we define a function called GenerateCommitMessage that takes a Git diff as input. Inside the function, we make our first LLM call using Generate Text to generate a raw commit message from the diff. We define a list of prefixes like feature, fix, docs, and check if the commit starts with one of them and is long enough. This gate ensures the message meets conventional commit standards for clarity and compatibility with the tooling. If it doesn't, we make another LLM call with clearer formatting instruction. The second prompt improves the result by setting expectation for the structure and clarity. Finally, we return the improved message or the original one if the quality check passed. Now, chaining handles step-by-step flows. But what if the step depends on what a user has asked? That's where routing comes in. Here, the user sends a query. It might be something like fix this code, write something creatively, or search for something specific. That request hits the first LLM. It takes the request and figures out which is the next step would be the best case. In our example, we have 3 LLMs ready to go. Once the LLM classifies the query as one of those types, we route to the most appropriate model. That makes the whole system smarter, more flexible, and more accurate. Routing works best when inputs vary in type or goal, you want to balance costs, speed and accuracy, or you're handling domain-specific tasks that benefits from model specialization. Now let's take a look at a code example. We import the necessary modules from the AI SDK. 3 LLM models, Generate Text, Generate Object, and Zod. We use Generate Object to classify the query with structured output. We define a Zod schema that classifies the query as either code, creative, or search, along with a reasoning string. Then, in our handled query function, we send the user query into classification step using Generate Object, with the model, the schema, and a detailed prompt explaining the 3 types. Once we get the classifications, we use model map to match the type to a specific model. Claude for code, GPT 4.0 for creative, and Gemini for search. You can do whatever you like with it, but this is just an example. We also provide a fallback to GPT 4.0 mini if the classification doesn't match. Then we pass the original query to the selected model using Generate Text and return the final response. This updated workflow allows dynamic routing based on task type, while keeping classification, model selection, and text generation as distinct steps. Routing is about choosing a direction, but sometimes the best direction is all of them. That's where parallelization kicks in. Let's say a user submits a piece of code. Instead of asking one LLM to do everything, we split the job. One model looks for security issues, another checks for performance, and another reviews maintainability. There is no gate here. Instead, we collect all the results in an aggregator and pass it to something like a summarizer to generate one final clean output. This workflow works best when you want to speed things up by running subtasks in parallel. If you need multiple perspectives or evaluations, or if each piece benefits from an isolated focus, like performance or readability. Let's quickly break down the code for this workflow. We start by importing OpenAI, generate text, generate object, and Zod, and set up our GPT-4o model. We define a function, review code, that accepts a code snippet. Inside the function, we launch 3 parallel model calls using promise.all, each one with a custom system instruction and a Zod schema for security issues, performance bottlenecks, and maintainability. Each call uses generate object to extract a list of issues specific to that domain. We then normalize the output using the type tag and merge everything into a single array called all reviews. Once those are returned, we pass the combined results to the final generate text call. This time the model is prompted as the technical lead, summarizing all the feedback for better readability and understanding. Finally, we return the structured feedback and the summary. As you can see, parallel workflows are great for multitasking. But sometimes you want precise control over how a task is done. That's where Orchestrator workflows come in. Again, we start with the user wanting to implement a new feature. We now hit the Orchestrator. Think of it as a project manager. It takes the main goal and breaks it down into multiple smaller jobs, like creating files, modifying others, or deleting some. Each subtask is handled by a separate LLM tuned for that job. These calls run in parallel, and once they're done, the results are passed into the synthesizer, kind of like your lead engineer reviewing all the PRs and merging them all into one clear result. And finally, you return the output. Orchestrator workflows are best when you're dealing with workflows with multiple dependent steps, or when you're combining results with different sources, or if you want fine-grained control over the flow. Now let's break down a code example. We start by importing OpenAI, generate object, and Zod, and define our implement feature function. We pass generate object to the OpenAI O3 mini model, a strong reasoning model ideal for planning. We define a Zod schema that extracts a structured implementation plan, including a list of files with their path, purpose, change type, and the estimated complexity. We also provide a system prompt to guide the model as a senior software architect creating this plan. Now this next part might look a little bit complex, but it's actually simple. What we are doing is mapping over each file in the plan and making a separate generate object call for each one. We dynamically select a system prompt depending on the file's change type. For create, the model is asked to generate a new component. For modify, it's asked to carefully improve existing code. And for delete, it's told to cleanly remove the outdated code. Each of these calls also include a schema for extracting the explanation and the actual code. Now, each file-specific implementation call is handled independently and runs in parallel using promise.all. This is for efficiency and speed. Finally, we return the object with the original plan and the individual changes array, each containing the file and its generated implementation. Finally, sometimes a single pass isn't enough. You want to iterate and improve. This is where Evaluator optimizer workflows come in. We start with the user submitting some code. In our example, the first step is generating a comment using an LLM. Then, we move to the evaluation step. Another LLM gives the comment a score. How clear it is, how correct, is it useful? If it scores well, we're done. But if not, we pass the feedback into another LLM call and improve it. That's the optimizer step. This loop continues until the comment meets the quality threshold, or until we hit a maximum number of attempts we set with max tries. This is a safety check to help us avoid infinite loops and wasting tokens if the comment never reaches the desired standard. Use this workflow when you care about quality control and iterative feedback loops, when you want to enforce a specific criteria, or you're aiming for high stakes or polished output. With the final workflow done, let's take a look at the code. We import OpenAI, generate text, generate object, and Zod. Then we define a function called improve comment that takes in the block of code. The first step is generating an initial comment with generate text, asking the model to behave like a helpful developer writing a clear, concise comment. Next, we kick off a loop. In each round, we evaluate that comment using generate object. We define a schema to capture clarity, correctness, helpfulness, and also list out any issues or suggestions. If the evaluation scores well, in our case higher than 8, then the loop stops there. If not, we pass the current comment and the feedback to the second generate text call, this time asking the model to improve the comment based on those suggestions. This loop runs until the comment meets our quality threshold or we hit the maximum number of attempts. In our case, it was 3. And finally, we return the structured feedback and the summary. Alright, and that's it for this video. If you found it helpful, hit like, subscribe, and drop a comment if you have any questions. And next up, we are diving into Vercel's AI SDK from the ground up. So I'll catch you in the next video.